So science and science climate change in particular has a lot of history behind it, and the science behind climate change starts with understanding physics and starts with understanding chemistry. And chemistry and physics, along with a lot of other primary sciences like geology and ecology, were really blossoming and becoming very robust in their mechanism of testing theory and being very clear about the rules behind science and the uh, minimization of bias. And so by 1895, it was really very much understood through repeated study and testing that certain gases bring about changes in the climate. So you add CO2, temperatures go up in the laboratory. You remove CO2, temperatures go down. We see the same thing with methane, the same thing with water vapor. The relationships, when you add those compounds, temperature goes up, temperature goes down when you remove those compounds. So very well understood for a very long time now. By 1896, it was postulated that humans are actually responsible for adding CO2 into the environment, and that because of the understanding from the 1850s that that the warming that they were measuring in the environment could be attributed to human emissions. All right, I'm going to skip over some of these because I tend to talk a long time on all of them, and I know that you guys can read up on them, and I can give you more resources if you want to reach out to me if some of this sounds interesting to you. I'm going to move ahead through to the 1930s. We're going to talk about Milankovitch cycles from the 1930s, but it was in the 1930s then that we moved from understanding the changing temperature as being from human causes to that the planet and the earth, or pardon me, the planet and the sun have a relationship, and that the orbit around our sun influences warm and cool periods, and that these orbital changes have caused past ice age scenarios. So if they cause ice ages, then the changes that go about with orbits then can also move our planet out of ice ages. And we've known through geologic studies, through hydrologic studies, and cryogenic studies, the genesis of ice, all right, when I say cryogenics, is that we have moved out of an ice age period. We've known that for the better part of last century. So moving into the 1960s, our science becomes more sophisticated, and we start to recognize in about 1965 chaos theory. And the principle behind chaos theory is very, very small changes can have very large results. So in the climate system, just a little bit of change in a compound such as CO2 or methane can result in significant results that last long periods of time. But under certain conditions, the nature of the change can be unknown. So for instance, if we change the albedo in different parts of the planet, that change in albedo may result in a quicker warming or a quicker cooling than it would if the albedo was changed somewhere else. So there's variability in the system. All right. So chaos theory becomes an understanding that a lot of what happens with the planet is not always as predictable as we thought our science could articulate. 5 years or so later, we start to recognize that aerosols, so particulate matter in the atmosphere, can counter climate change. So if you put a lot of dust in the atmosphere or pollution compounds, they result in more refraction. We've talked a little bit about this semester. That refraction is going to limit the amount of solar insolation which is going to get to the surface of the earth, and consequently, if it doesn't get to the surface of the earth, it can't warm the lower volume or lower reaches of the atmosphere, which means that the earth isn't going to warm. So when we were very much an industrial nation, post World War II, we had more particulates, aka aerosols. Temperatures were a little bit depressed. We see the Clean Air Act, temperatures start to go up because now those aerosols are not acting as agents which are going to refract incoming solar energy back out into space. So, but that's only one variable, all right, you guys? That's not a catch-all for everything. It's not a silver bullet. By 1974, that study that came out that my mom got excited about that said we're going to enter an ice age takes hold. Ask some grandparents, if you will. Do you remember the 70s when they said this? And maybe they were very much like my mom and went on a binge to go shopping for snow gear. But the journalists who were talking about the ice age got a lot of people excited. That very next year, computer models, because the computer science is improving, are saying, wait a minute, we're not cooling the way that study that just came out said. We're still on a warming track. CO2 is still going. And the next year, chlorofluorocarbons and methane are going to are not going. They are contributing to the greenhouse effect. We're seeing sea cores added to the cores from the 1960s, which were confirming some of those orbital changes from the 1930s, starting to show that we've got a feedback mechanism, that things play off of each other. And we'll talk about feedbacks in a little bit here, all right? By 1981, the personal computer is introduced, and that's where we get this really big blossom of more people working on trying to understand science and climate change science in particular, because that's what this unit is about. All right, so we've had, by this point, the better part of 160 years where the science is becoming more and more refined, and we've had scientists try to pull this stuff apart. Remember, it's their job, and they want to be the guy that goes down in the history books that said, this is not the way we thought it was going to be. Everybody wants to be the proverbial Sir Isaac Newton, who puts us on a new track, right? There are egos involved.